Hello and welcome to this video lecture on conditioning of continuous random variables. We will start by defining the notion of conditional expectation for continuous random variables conditional on the occurrence of an event. So let x be a continuous random variable on a probability space omega fp. The expectation of x conditional on b is defined as the expectation of x times the characteristic of b divided by the probability of b. I will explain what the characteristic is in a moment. This definition only makes sense if the probability of b is non-zero. The characteristic function of a set b is a random variable denoted by 1 subscript b, and this is equal to 1 if omega is inside b and 0 otherwise. If x has a probability density function, we can define the conditional density of x given b. This is defined as 1b times the PDF of x over the probability of b. The conditional density can be used the same way as a familiar unconditional density function. This is what this means. Look, the expectation of a real valued random variable x given b is the integral from minus infinity to plus infinity of x times the conditional PDF of x given b. This should be reminiscent of the way we can use a PDF to determine the expectation of x, the unconditional expectation, so you see the similarity. Here is an exercise you can try for yourselves. Suppose that x follows the standard normal distribution with mean 0 and variance 1. The question is, determine the expectation of x conditional on the event that x is larger than 2. All you have to do here is take the definition, write it down, use the fact that x follows the normal distribution, so you know the density function, and this way you can determine this conditional expectation. We can now also condition a continuous random variable on another random variable. Let x and y be two real valued, or can be even vector valued, continuous random variables, and they are defined on a probability space omega fp, and we have the joint density function of x and y. This is denoted as p subscript x comma y, and this is a function of two variables, x and y. The conditional density of x, given the fact that y, the random variable, is equal to a value y lowercase, is defined as the joint density function divided by the marginal density of y, provided of course that the density of y is not equal to 0. Note here that the conditional PDF of x given y depends parametrically on the given value of y. So the conditional expectation of x given the fact that y is equal to y is the integral of x times the conditional density of x given y, and the integration is of course with respect to x, while y is a given value of the random variable. So the right hand side we see here depends parametrically on y lowercase. We can also define the conditional variance of x given y. We just need to take the definition of the variance of x and replace all expectations by their conditional versions. Recall that when we defined two events a and b to be independent, we said that they are independent if the probability of their intersection is the product of their probabilities. We say that two random variables are independent if their joint probability distribution is the product of their individual distributions. To put it in other words, if the probability that x is in a and y is in b is equal to the probability that x is in a times the probability that y is in b. Equivalently, we can say that x and y are independent if their joint PDF is the product of their PDFs, or equivalently again, if the knowledge of any of the two does not alter the distribution of the other. In other words, if the PDF of x given y is equal to the PDF of x. Let us highlight some of the most notable properties of the conditional expectation. Firstly, like the expectation, it is a linear operator. The law of total expectation is a very useful property. It states the following thing. The expectation of the conditional expectation of x given y is equal to the expectation of x. In very simple words, what you expect x to be is what you expect x to be after you learn y. So what you expect x to be now is what you expect it to be after you find out y, but you don't know the value of y yet, of course, in either of the cases. Next, we can pull out constants from the conditional expectation. If we have the expectation of g of y times x given y, then g of y behaves like a constant and can be moved out of the conditional expectation. As we said before, if x and y are independent, the expectation of x given y is equal to the expectation of x. Another very useful property is that the conditional variance of x is given by this formula. This is very reminiscent of a very similar formula we had for the unconditional variance. So the formula for the unconditional variance is the same like this one if you remove the conditioning given y. So we have that the variance of x given y is the conditional expectation of x squared given y minus the expectation of x given y squared. So it's really similar. The law of the unconscious statistician has also a conditional version. And lastly, we have these two properties which will turn out to be very useful. The first one allows us to take the expectation of functions of random variables x and y, and the second one is the application of the law of total expectation on functions of x and y, on g of x and y. Let us move on to a very important example that will play an absolutely central role in understanding how the Kalman filter works. So suppose that x is a multivariate normal random variable, or Gaussian, as we say, random variable, with given mean mu and given variance covariance matrix sigma uppercase. Let us split x into two vectors, x1 and x2. x1 has a dimension n1, x2 has a dimension n2. And we can segment likewise mu and sigma as shown here. Let's see how we have segmented sigma. Sigma 1, has dimensions n1 by n1, and sigma 2, has dimensions n2 by n2. We shall assume that sigma 2 is positive definite. Then the conditional expectation of x1, given that the random variable x2 is equal to a value x2 lowercase, is given by this equation. We will not give a proof of this result. Note that if x2 is exactly equal to mu2, that is if x2 is equal to the value we expect it to be, the conditional expectation then of x1 is exactly equal to mu1. Note that the conditional expectation of x1 given x2 is a function which is affine in x2. It is a function of x2 which is affine in x2. The conditional variance of x1 is given by sigma 1 minus sigma 1 times the inverse of sigma 2, which exists because sigma 2 is positive definite, times sigma 2, Since sigma 2 is positive definite, the matrix sigma 1 times the inverse of sigma 2 times sigma 2 is positive semi-definite. In other words, additional information does not quote-unquote increase. I say quote-unquote because these are matrices. We cannot exactly compare matrices, but we can say that one is smaller than equal the other if their difference is a negative semi-definite matrix. So in the sense of the inequality symbol that we use here, we can say that additional information does not increase the variance. And with that we have concluded this first part, which was an introduction to probability theory. We will move on now to estimation theory, and in the next video lecture we will give an introduction to minimum variance estimation. Thank you very much for watching, and goodbye.